Okay, so yeah, so 4.4 is just looking at acids and bases. So you guys need to know like the characteristics of acids and bases, so how they're different basically. And yeah, you should just know the main differences between them. You should know what a strong acid is compared to like a weak acid. Basically, if you guys remember that video I showed you, like strong acids are acids that are more reactive, they're more corrosive. So if you were to be in contact with a strong acid, it would burn you, whereas a weak acid is an acid that's kind of safer and less reactive because it's we usually find these acids in our food, like in lemon and vinegar and stuff. They're things that we are safe for us to consume or get into contact with. So you're just knowing the difference between strong and weak acids, and just some characteristics of acids in general. The same thing for bases. And we used a memory tip, bases accept, acids donate, to remember that in terms of, the donation or the acceptance of a hydrogen proton, acids tend to donate a hydrogen proton and bases tend to accept. So that's just how they operate on a chemical level. So if you just remember that memory tip, in case, it's asked in some question, then you'll be able to remember which one does which. Then that's just the pH scale. So you just need to remember that bases tend to have a pH of more than 7. Acids tend to have a pH of less than 7. And right in the middle, you've got your neutral substances there, or the neutral level. Neutralization reaction. So this is really important. You guys need to be able to understand that when you combine an acid with a base, and usually a base is some kind of metal hydroxide, for example, sodium hydroxide is a base, and you combine that with an acid like hydrochloric acid, for example, you'll always have the products being water and a metal salt. So that metal salt could be potassium chloride, could be magnesium chloride, could be sodium chloride. You'll have some salt there along with water. Okay, that's the basic formula. And remember when we did that worksheet, we did like 3 pages of equations on that worksheet with the little smiley face on it. That was all about neutralization reactions and then reactions with metal carbonates, and how when you combine an acid with a different item like a metal carbonate versus a metal hydroxide, the products are different. Okay, so just remember that main rule there, that an acid plus a base will give us the 2 products of water and a metal salt. So that's basically what you need to know, and that's called a neutralization reaction. So that's basically what that's called. And remember, neutralization reaction is a type of chemical reaction, similar to our synthesis reactions or our decomposition reactions or our combustion reactions. Neutralization is just a type of reaction. So if you guys ever see a reaction and the products of that reaction are H2O, just turning this into a chemical formula, plus, for example, a metal salt like magnesium chloride, for example, so MgCl2, then you would automatically know that that was an example of a neutralization reaction, because those 2 products are typically found in neutralization reactions. Okay, just important for us to be able to differentiate and understand when a reaction is neutralization, or when it is synthesis, or when it is decomposition. So anyway, we did some examples of these together, and you've got the examples of what these look like in your book. Just to recap, if I can find my worksheet, then I can show you guys. I can write down the formulas again for you. Give me 1 second. Also, something else I need to mention is that you guys, I think I posted it on the school box as well, but you guys will be getting all the tables in your test. So you don't have to memorize the polyatomic ions like sulfate and stuff. You will be getting that on the actual test. So we'll put that right at the beginning on the first page. So, it's already written here. What am I doing? Okay, hold on. So as you can see here, when an acid and a metal combine, usually the products are salt and hydrogen gas. So the salt is a metal salt like magnesium chloride or sodium chloride. When an acid and a metal oxide react, they will form products of metal salt and water, okay, as we saw in the previous slide. And that's a neutralization reaction. just going to write neut. And then when an acid and a metal carbonate combine, because remember the word carbonate has the word carbon in it. So just remember, again, it's a metal salt, like magnesium chloride, for example, water, H2O, and carbon dioxide is the extra product we have here. Because remember, the carbon and the carbonate. So carbon and carbon, obviously, carbon dioxide is additional product when an acid and metal carbonate combine. So metal carbonate means, for example, calcium carbonate or potassium carbonate, any carbonate that has a metal in front of it. Okay, and we know our metals are usually in, group 1, group 2, group 3 to 12. Those are where our metals are located. So any metal, insert metal name, and carbonate is basically what we call as a metal carbonate. So if an acid like hydrochloric acid is to combine with a metal carbonate like calcium carbonate, usually what would happen is we would have salt coming out of that, we'd have water, and we'd have carbon dioxide. So that's just talking about the typical products that are formed in your common acid reactions. So acid metal oxide, and acid metal carbonate. So those are the three types. That's why our booklet was 3 pages, because remember we had 1 page just talking about how to write up equations for acid metal, and another page for just acid combining with a metal oxide, and then the 3rd page was acid combining with a metal carbonate. So if you guys have that worksheet, just go through that again. I'll see if, I think I left my copy at school, but I'll see if I can scan the answers from that and maybe upload it on Schoolbox tomorrow. We can have a look at it during class in case you forgot which one I was talking about. All right, so that's basically, that's basically the common acid reactions and the rules. So these are our reactants. Sorry, I forgot to mention. These would be our reactants, or an acid plus metal combining, and these would be our products in red for each type. Okay. Okay, so that's basically talking about the acid reactions. Then we talked about concentration of a reaction. We talked about usually the concentration talks about how much molecules of that acid or base are present in each liter of solution. The more molecules of that acid or base you have, the more concentrated it will be. And remember, we talked about the cordial analogy, saying that if you just pour full cordial syrup and don't put much water in it, we say that that's quite concentrated because it's quite thick. You can see that it's darker in color compared to the diluted one that's got more water mixed into it. Okay, so obviously, and a strong acid is an acid that's quite reactive. And what we mean by reactive is that it will really quickly donate a hydrogen ion to a base. Remember, we said bases accept, acids donate, that memory tip. So just remember, acids always donate, and how quickly an acid donates will be dependent on how strong or how concentrated that acid is. And the same thing goes for the base as well. Now, acids are stored in glass bottles. This was a question in your book. Acids are stored in glass bottles, obviously, because if we were to store them in a metal container or a metal tray, the problem would be that the metals and the acids would react with the metals and corrode the metal away, which would be quite dangerous. Okay, those are reactions. Reactions. Those are just the summary of the 4.4. So any questions about 4.4?
Yeah, you see how you said that they will react differently with metals? What if you store them in a plastic container?
Plastic would be okay, because plastic doesn't rust in the same way that metal does. But then the problem with plastic is that something called leaching can occur, where, for example, when that acid is poured into the plastic, it can actually eat away at the plastic or the polymer molecules. So it's actually still quite dangerous. Yeah.
Miss?
Oh, okay.
Yeah.
You know, for the last test, we had like that paper thing and we had to draw on that. Are we going to have something like that in this test?
Paper thing? Which paper thing?
When we had to draw the atoms.
The ionic bonding and the cationic bonding and stuff?
Oh, no. So that and ionic bonding and electron transfer diagrams, those were specific to chapter 3. We won't have any of that in the test, but you will have that in the semester exam. Okay, because the test is only on chapter 4, so we won't have any covalent bonding. You will need to be able to write your chemical equations. That's something we will need to do, but other than that, yeah, I don't think you have to draw. There is no electron transfer diagram or covalent bonding. No, that's all chapter 3, so we won't be assessing that. Okay. All right. Any other questions about acids or bases before we move on? No?
No. Will my test be different to everyone else's test, or will it be the same?
Yes, of course. So Mariam and
Different.
test will be different to the test on Wednesday. Okay.
Okay.
It's not going to be harder. It's going to be the same level of difficulty, similar topics, but just the questions will be different.
Do we have less questions as well?
Not significantly so, but I have removed one question out.
Okay.
You will have enough time. Don't stress. All right. So I'm just going to close the acids and bases and open up. I think 4.5 was about precipitation reactions. Yes, it was. Okay. Now let me quickly share the screen again. So I'm on the right one. Okay. Is that showing up as 4.5 for everyone now?
Yeah.
Yeah. Okay, good. All right. So 4.5 was just talking about precipitation reactions. And this is what we did our prac on as well. So just remembering that a precipitate is always insoluble, and insoluble means that it doesn't dissolve in water or any aqueous solution for that matter. So a few things to remember is a precipitate is insoluble and that it's a solid. So when we talk about precipitates in terms of states of matter, they are always solids. So if we look at our typical equation, precipitate is usually AD. We know that the precipitate is AD because that's the only compound in this chemical equation that is solid, okay, represented by S. So when you guys are writing your chemical equations in the test or even in the exam later on, make sure that you don't make that same mistake you all made in the prac. Make sure you write the clear states, okay? And usually in the test or exam, it will ask you to write a full balanced equation. Okay, what we mean by full is you have to include the state. Even if we don't mention the word full balanced equation, if it's asking you for an equation always includes the states. Okay, so be really careful here. When you read the question, whenever you're asked to write a full equation or a balanced equation, it must include the states. In the case of precipitation reactions, it's quite easy. All you guys have to remember is every single compound in there will be aqueous except for the third one, because the third one is our precipitate. That will be solid. Okay, now if you guys remember the formula, AB plus CD gives us the products of AD, the precipitate, plus CB, it will be easier for you to be able to write your precipitation equations and identify what the precipitate is if you're given an equation. Okay, so that's just what this is explaining here. So the positive ions, which are A and C, are always written first. So what that means is that if your symbol is AD, it's hard to explain this without an actual thing, but let's say that D was chloride and A was potassium here. You'd have to write potassium chloride. You can't just write chloride potassium because the positive ion or the cation has to be written first. Okay, that's just one of the rules of writing chemical equations. Now this is called, and remember I mentioned this when we were going through this, this is an example of a double displacement reaction. That basically means, this is again another type of reaction similar to our synthesis, combustion, decomposition, neutralization. It's just another name for another type of reaction or chemical reaction. So what happens is, because we're swapping, remember I said A from this kind of joins this and they form one compound, okay? And here the B and the C, or the C and the B, will combine another one. That's called double displacement because both of those substrates or both of those little parts of those compounds are actually swapping, or they're displacing. So A is going from one partner to another partner, joining AD, and then B and C are kind of joining together as a new partner of CB. Okay, so that's what double displacement means, that there's a double swap or a double displacement. Displacement means when you go from one place to another place. Okay, so that's basically, it's like a little switcheroo kind of situation there. Okay, we've already described this. This is just explaining that formula there. Is there any confusion about this formula? This formula is used for precipitation reactions. Okay, so if you're given a formula where there's clearly a solid in this placeholder here, the third position, and everything else is aqueous, you should automatically know that that is an example of a precipitation reaction. Because precipitation reactions demonstrate this concept of double displacement, where you have, the substrates kind of swapping partners. So A moves away from AB and says, okay, B, I don't like you anymore. I'm going to go join D, A, and becomes AD. Precipitation reactions are sometimes also called double displacement reactions because that's what they are. precipitation reactions and this formula here demonstrate the idea of double displacement. So sometimes these two words, precipitation and double displacement, are used interchangeably. They kind of refer to the same thing. Okay, so that's basically the formula for precipitation reactions. So guys, this table here, you will be getting this table in the test. So this, again, like I said, this will be right at the start of your test on the first page on EP. So you will be able to come back to this and refer back to this at any time. I think by now, all of you should know how to read this table. It's the exact table we're giving you. It's not from a different book. It's the exact purpley one with the 3 columns that you're going to get in the test as well. So hopefully you should.
I don't understand that table.
Okay, which part of it don't you understand?
I don't know. I just don't know what it is.
Oh, okay. So it's talking about the solubility. So solubility means to what extent elements or compounds dissolve in water, in an aqueous solution, because water means aqueous, yeah? So whenever we're talking about aqueous, oh my God, I think I just forgot. No, I remember how to spell aqueous. Sorry. I thought I forgot how to spell. Aqueous basically means, I think there's a U there. Okay, aqueous basically means whether these elements will, or these compounds will dissolve in water. So the first column here talks about solubility. Okay, soluble means that these elements, I can't write properly, but I'll try, are dissolvable. Okay, that's not really a word. Dissolvable means that if you were to put these in water, in like element form or compound form, if you were to put these in water, they would dissolve. Remember when we were doing our prac and I put some of those compounds in the test tube, those compounds didn't really change color. They didn't really show any forms of cloudiness. They didn't show any kind of jelly-like formation. It just simply became clear. Yep.
This one, soluble, does not form a precipitate, yeah?
Yes. So soluble ones, yeah, exactly what I was going to say, Hannah. They do not form a precipitate. Okay, so they will not and they do not form precipitates because a precipitate is an insoluble solid. Yeah, that's what we said the definition of a precipitate was. So it's an insoluble solid. So this column here, the second column, they do form precipitates most of the time. Okay, obviously we talked about the factors that can affect that. For example, concentration and the temperature of the room or temperature of the test tube and all that stuff. So just the most important thing for you guys to remember is when you're reading this table, everything in the first column here, the soluble column, these are dissolvable in water. They do not form, I'm not going to write precipitate, I'm just going to write P. They do not form precipitates. The insoluble, the middle column there, they do form precipitates, okay? So we're talking about group 1 elements here. And remember that if you have a group 1 element and it's attached to a salt or it's attached to something, it's not going to form a precipitate. So for example, lithium is a group 1 element. If lithium combines to chloride, they're both soluble, so they're not going to form a precipitate. In most cases, if lithium is even combined to a sulfate, the chances of that forming a precipitate are also less, okay? So this is just there for your understanding. And we said that most things, like with the exception of silver and lead, okay, when silver combines to chloride, just because of the way that it operates when the two come together, silver chloride is actually going to form a precipitate, and the same thing with lead.
Miss.
Yep.
You know, on the prac, the first question, the table, how
Yep.
there was like rows and columns of like chemical thingies, elements, whatever they're called.
Yep.
And then we had to try to guess if that would form a precipitate or not. Will that be on the test?
No. That was just for the prac.
So what sort of question will we expect to get from this table? Like,
so we might ask you, for example, we might give you like a list of compounds and then ask you which one of these is likely to form a precipitate, or we might even ask you which of these are likely to be soluble, that is, do not form a precipitate. So then whatever we give you, you have to refer back to this table and then you have to make a judgment. So if it's a 1 element, you would say that yes, it's soluble. If the question was asking which of the following will form a precipitate, and we gave you, for example, silver bromide, you can see silver bromide is in the insoluble column. So then you would say, yes, silver bromide would form a precipitate.
Miss,
something with the, if we gave you a carbonate compound, like let's say, magnesium carbonate, okay? be an example of an insoluble compound. Okay, so that's basically what we're talking about. It's just your ability to read this table and cross-check with the question or the compounds we have given you and make a judgment based on that. But we're not going to give you a huge table like what we did in the actual practical. That's too time consuming. We don't have time for that in the test. Okay.
Okay, thank you.
No worries. Okay, so yeah, that's basically, and guys, remember we had this memory tip as well. So Snape rule. So all your sodium is an example again of a group 1 element, nitrate, ammonium, potassium, and ethanoate. Ethanoate, we're not going to focus on too much, so don't stress about that one. Those are all like, that's a memory tip for you to remember some of the soluble elements and compounds. And the Snape rule only applies to the first column of soluble elements and compounds there. Okay, so that's basically yeah, just the solubility table, which you will get in the test, and you don't have to memorize this table. Okay, so remember I showed you guys just this example of copper 2 sulfate and sodium hydroxide combining. So if we were to give you this kind of an equation and give you the states, you should be able to say that this is, for example, a precipitation reaction or a double displacement reaction. So you should be able to classify based on the products involved in the states, what is a precipitation reaction and what isn't. Okay, so just be familiar with that and have a look through again over your, your book and the formula for precipitation. Okay, so one more thing to mention is that precipitates are not always like, don't always lead to a change in color. So although in our particular prac, when we did it, whenever copper sulfate or copper nitrate combined with a solution, you guys might remember there was a bluish color. That's because naturally, when we're talking about copper tends to be blue when we store it in aqueous solution. Okay, so that's the natural color of the copper. But precipitation doesn't always need to be a change in color. So here, for example, although his solution in this GIF is blue, precipitation could just be a cloudy white substance. It could just be a jelly-like clear substance that's floating in the water. As long as it's solid and as long as it doesn't dissolve, that is, it's insoluble, it would classify or it would qualify as being a precipitate. Okay, it doesn't have to be a sparkly, beautiful new color that's formed there. Okay, so color change is not a major qualifying factor in order to be a precipitate there. Okay, so these are just some examples from the book of what a worded equation for a precipitate is, and then what a chemical equation looks like. So you can see that this is the worded equation here. In case you guys forgot what the Roman numerals are for, so I told you guys that some of our transition metals in our periodic table, they have variable charges, variable valencies. What that means is that depending on the chemical equation they're placed in, they could have a +2 charge, and they could have a +3 charge. Okay, so we know certain ones, like in the periodic table, like calcium has 2+. We know that's a kind of set. That's set as in that is usually always true. Okay, we know that, for example, lithium has a +1 charge. That's also kind of set, okay? And lithium is in group 1, calcium is in group 2, which is why lithium has a +1 and calcium has a +2. But when we're talking about other metals, particularly our transition metals, if the charge is not given in the periodic table, it's not clear, usually what we do is we put the number in the brackets. So if you have a Roman numeral number 2, for example, what's going to end up happening is that we are going to have oops, sorry, what happened to my screen? That's going to be that's basically meaning lead with a 2+ charge. Okay, why is it 2+? Because lead is a metal, and most of our metals are of, a cation classification. They have a plus charge. So lead, Roman numeral 2 means lead 2. Same thing with copper. If you see Cu 2+, that might also be written as copper 2+ in Roman numerals. Okay, so you'd have copper and then you'd have a Roman numeral in the brackets. Same with any number. Okay, so that's basically what we're talking about when we're talking about the Roman numbers. So here we got lead 2 nitrate, lead 2 nitrate plus potassium iodide equals to lead 2 iodide plus potassium nitrate. So that's just following the same formula that we just talked about before. So just give me 1 second. Yeah, so that's just following the same formula we talked about before. So we've got our AB plus CD, and that's going to be AD plus CB there. So that's basically what they're showing. And they've written all the states, which is correct. And the big twos there in front of the potassium nitrate and potassium iodide are the balancing. Okay, so we all should remember how to balance. It's just counting the number of atoms on the left-hand side of the equation. So in this case, counting the number of lead atoms, counting the number of nitrogen, oxygen, and iodine atoms. Okay, so remember, we don't count it like this. We don't count nitrate as one big atom. We have to divide that into N equals O equals like that, okay? Because that's a polyatomic ion that's made of multiple atoms of different elements there. So we have to always break it down and make it simple, okay? Not just clump everything and count it as one. So yeah, that's just basically showing you the worded equation. Okay, let me just, so that's the worded, that's the one you guys are really good at doing. And I think all of you got this one right anyway in the test and stuff, in the prac, sorry. This is the chemical equation. This is the one a lot of you struggled with in the prac. Just a lot of you forgot to mention the states, and some of you also forgot to balance. So remember, states need to be there. The balancing has to happen as well. Sometimes you don't have to balance, but it's always important to double check before guessing that all balancing doesn't have to take place. Okay, and this is basically the ionic, sorry, lost my word there for a second. This is the ionic equation. Okay, ionic equation means it's an equation for only the precipitate, and you're showing which two elements or which three elements or however many you're working with have actually joined together to form. So this is the precipitate here, and the ionic equation just takes the precipitate and breaks it down into its individual ions. Okay, so if we look at this, this is lead iodide. Okay, lead iodide is made of lead, which has a 2+ charge. We know that it's 2+ because remember the Roman numeral 2+ there. And iodide. Okay, iodide we know is one of our nonmetals. Okay, and iodine, which is where iodide comes from. Iodine usually has a -1 charge, which is why it's -1 there. The reason we've got a big 2 here is because when we do the old switcheroo, if I can draw my switcheroo here, remember we talked about putting the charges side by side, and if they're not the same, then we have to swap them around. Okay, so then when we do the old switcheroo, it's like PB. So PB takes the -1, and we don't write -1 here, because for 1, we just leave it as it is. And that'll be I2. So the 2 comes from iodine taking the charge of lead, or PB there. Okay. And then
you see when you write it
Sorry?
like that, when you're writing the ionic, you see like that formula? See how you're adding the charges?
This one?
Yeah.
Yeah.
Like the PB 2+ thing, the formula. When it's saying for ionic reaction, do you have to write it like that? You have to make sure you add the charges?
Yes, you have to. Yeah, you have to. Because remember, guys, and this is the main thing I was telling you guys in class, whenever something says ion or ionic, ion or ionic means that the charge has to be there. So it's either positive, negative, or both. Okay. So if it's just a normal chemical equation, here, for example, we don't write the charges. Yeah, we just write it without the charges. But an ionic equation is called an ionic equation because they want you to talk about the actual ions that are involved. And ions are a charged atom. Okay, it can either be a cation in the case of lead here, which is a 2+ charge, or it can be an anion in the case of iodide here, that's a -1 charge. Okay, so that's what you're doing. You're taking the precipitate. The precipitate is the right-hand side, or it's the product that's formed in an ionic equation, and then you're working your way backwards. So first thing in an ionic equation, of step 1, write the precipitate from your chemical equation here, take that and put it on the right-hand side. Put the arrow then, okay? And then you only have to fill in the left-hand side, which is here. And this part here, guys, is just breaking down the precipitate into the 2 ions that it's made of, okay? So if my precipitate was sodium chloride, like that.
Synthesis.
Sorry?
That's the example of a synthesis reaction. Yeah, the 2 parts.
Yes, it's similar to that. Yes. Okay, so then when we're talking about so if my precipitate is sodium, for an example, And I've written that down on the right-hand side of the arrow. Yeah, that's my step 1. Step 2, fill in the left-hand side of the arrow. So I know sodium chloride is made of sodium, which has a +1 charge, okay, and chloride, which has a -1 charge. Obviously, I can write -1 and +1, but usually if it's plus, that means +1, okay? We know that. So then all I need to do is just write down the formula here. So that's aqueous, and as with everything else, my precipitate, which is here, is going to be solid, okay? So that's exactly what's been reflected here. Okay, so if you're asked to write an ionic equation, you take the precipitate and break down the precipitate into the 2 ions that it's made of, okay? Because remember, whenever we have a compound is always made up of 2 or more ions, okay? 2 or more ions. That's why we call it a polyatomic ion, because it's made up of 2 or more. And all of our things that we've been learning, sulfate, carbonate, lead iodide in this case, these are all examples of polyatomic ions because they are made up of 1, 2, or even more than that in terms of the atoms, okay? So does that make sense? Do we know the difference between worded equation, chemical equation, and an ionic equation? Yes, hopefully. Okay.
Yeah.
This is just giving you another example. Again, whenever you have the numbers in brackets like that, that means copper has a 2+ charge. Okay. The reason that copper 2 combining with sulfate here forms CuSO4 rather than Cu2SO4, remember guys, is again the switcheroo. So if we've got Cu, it has a 2+ charge, and SO4 has a 2-. So when we write this down in our chemical equation, 2 and 2, 2 minus 2 is 0, the net charge is 0, there's no switcheroo happening, okay? It's just going to be CuSO4, just like that. Okay, so be careful, guys, when you're writing your balanced equations, you have to make sure you are doing the old switcheroo before you actually go. If you don't have to switcheroo and it just automatically goes like that and the charges cancel out to become net 0, then that's excellent. Sometimes that does happen, even in the case of sodium chloride. Sodium is +1, chloride is -1, so you just write it straight up like that, and that's correct. But in some cases, if the charges are different, it will be different. So you have to do this old switcheroo. Okay. So yeah, that's just another example. Again, this is another example showing you, again, an example of a precipitation reaction. Everything is aqueous except for silver chloride here. That's the precipitate. And we know that's the precipitate because it's the solid, the only solid compound in this whole chemical equation. Okay, so that's the main way you guys are going to be able to identify in the SAC or in the exam if something is a precipitation reaction or not. Okay, everything else is aqueous. Aqueous means stored in water, except for one compound in there is solid, and that solid is the precipitate. Hence, this is an example of a precipitation reaction. Okay, so now what do we have? Why is this showing up again? And these are just talking about the different ions, talking about basically the different charges that are involved. Okay, this is not so important though. It's just showing you like a more visual understanding of how it all works. Okay, so that's basically. Sorry?
Miss, what should we pay extra attention to for the test?
Mainly your equations. You guys need to just know how to identify the types of equations and also how to write proper equations. So I think skills like work on your balancing of equations, work on your even things like simple stuff like the old switcheroo. We keep forgetting to do that, and I need to stop calling it the old switcheroo. But for example, if we have, if I tell you guys to write the chemical formula for magnesium nitrate, for example, we know that magnesium has a 2+ charge and nitrate has a -. A lot of you would write magnesium nitrate like this. Magnesium nitrate. That's wrong. Okay, yeah, that's wrong because you're not doing the old switcheroo. So when you do the old switcheroo, you're switching the charges about. So you're going to say, okay, it's going to be Mg. Now, this is a -1 charge. Sorry?
The switcheroo, that's for balancing equations. What's it for?
You need to because we need to make sure that before we include in our chemical equation, the net charge has to equal to 0. Okay, so how the net charge here would equal to 0 is that they swap the charges around. That's just the basic rule of writing a correct chemical formula. Yeah, so see Mg takes on the -1 charge. We don't write -1 here, we just leave it as it is. And NO3 takes on the 2 there. Okay, so that's basically, and that 2 is from the magnesium. So just be careful when you're writing your chemical equations to make sure you're checking that the charge is equal to 0 before you're actually writing it in the chemical equation. Otherwise, you will get that part of the equation wrong. Okay, so I think that's precipitation's done. Yeah, that's just the, oh, one more thing, the spectator ions. So I think spectator ions are literally quite simple, just any ion or any compound that doesn't take part in the actual precipitation reaction. Usually everything except the precipitate is an example of a spectator ion. Remember, spectator ions are just ions that just watch, or, you know, like spectators at a sports match, they just kind of watch, but they're not actually involved in the actual formation of that precipitate. Okay, so everything except the solid precipitate there. I'm just writing SP. Okay, so those are our spectator ions. And remember, ions again, guys, you don't just write, okay, the spectator ions were NaNO3. That's not correct. If you do that, you won't get full marks. The reason being, what's the reason, guys? Why would this be wrong? Just as an example.
Because there has to be charges.
Yes, excellent. So I didn't add the charges. So I have to add plus and a minus there. Okay. It depends, whatever you're doing, whatever you're talking about. If your two things are calcium and sulfate, you would have to write, okay. You'd have to write 2 plus there and then 2 minus there. Okay. So whatever the charge is and whatever numbers attached to that charge, you must write it down. Okay. And we are going to give you the polyatomic ion table. So you will be able to refer back to that. So you don't have to memorize the charges for sulfate, nitrate, it'll all be there for you. But just make sure that you know this basic idea, that when it says ion, you must include the charge. All right, so that's precipitation reactions done. So I'm just going to move on to now 4. Oops, where is my 4.6? Okay. Okay, are there any questions about precipitation reactions?
Miss, you know, for precipitation reaction, for example, there's a compound that's the precipitate.
Yes, the
So
compound that's
other than the actual precipitate would be the spectator.
yes. So literally, like the ions that are not involved in the actual precipitation reaction, those are our spectator ions because they just watch. Hold on.
No, I mean, okay, Miss, for example, the precipitate is what can I precipitate?
Precipitate
Chloride,
is your solid insoluble solid substance. When we do precipitation reaction, it's usually the third compound in that equation, the first compound after the arrow.
Yes, and so okay, all right. There's a precipitate, yeah. There's like a little compound thingy element, whatever it's called. And then any other element or compound, a molecule or whatever that is not included in the actual precipitate precipitate compound, that is the spectator ion. So if there be a question, I'll just write that.
Yeah, so for example, if my products were silver chloride and sodium nitrate, just an example, random example, silver chloride would be my solid precipitate and sodium nitrate would be the other product. It's not the precipitate. So all I do is I take that sodium nitrate, which is aqueous form, and then I just divide that into sodium, which is one ion, one spectator ion, and nitrate, which is the other spectator ion. That's all I'm doing. Those are my spectator ions.
So there's 2 spectator ions.
Not always. It depends on the equation that you're given. There might be more, depending on how big your chemical equation is.
Okay, thanks.
At your level, guys, there will be mainly 2 ions that you'd have to write. Okay, so anyway, moving on to 4.6. So 4.6 was just talking about combustion. So we said that when an element reacts with oxygen, in the case of, for example, rust, in the case of corrosion, usually that's an example of an oxidation reaction. And we talked about the fact that a lot of the time our metals do form oxides. That's why before working with metals in the lab, we always rub the metal down with some steel wool to get rid of any rust that may have formed on the surface. So we talked about this at the beginning as well of chapter 4, but whenever you've got a metal combining with oxygen, it forms what we call as a metal oxide, okay? That's just the word given to a metal that has reacted with oxygen. Okay, now oxidation of metal, like I said in the previous slide, is a corrosion reaction, and oxidation reactions are exothermic. Okay, so you guys know what exothermic and endothermic are. You've learned about it in previous years as well. Exothermic is basically when you're releasing heat and you're taking that heat is going outside. So remember, exo comes from the word external, which means outside. So exothermic means any reaction that produces energy in the form of heat, and that heat is radiating out. Okay, endothermic is, endo means inside. Okay, so endothermic is basically any reaction that absorbs heat or light inside. Okay, exothermic is when it takes it outside. Okay, so that's basically talking about what exothermic is, talking about the fact that oxidation reactions and combustion are exothermic reactions. So we just talked about the fact that usually our nonmetals do react with oxygen, except for our noble gases, which are our group 18. We say they're noble. We say that they are generally quite inert or unreactive. They have a full stable outer shell of 8 electrons, which means that they generally do not react with oxygen, but every other nonmetal does. Okay, so don't worry about the pop test. That's not very important for the test. That's more of a thing we look at in the lab. Yeah, so I think that's nothing much there. Okay, combustion reactions. So just like decomposition, just like synthesis reactions, just like neutralization, just like precipitation, these are all types of reactions. Yeah, if we look at a chemical equation, we should be able to say, okay, that's an example of a synthesis, or that's an example of a decomposition, or so on and so forth. So whenever you've got a combustion reaction, you have to remember that a combustion reaction has specific products that come out of that. You also need to remember that when we're talking about combustion reactions, we're often talking about the fact that we are trying to create some kind of fuel, okay? Now, the main or the most common type of fuel that's used to produce energy is hydrocarbons. Hydrocarbons are given this name because they're basically made up of hydrogen, hydro, and carbon, which is carbon, okay? So hydrogen and carbon are the two main elements that make up our hydrocarbons, okay? And when we burn hydrocarbons and when combustion reactions take place, like when you light a fire, for example, you would realize that you are creating a large amount of useful energy. In the case of fire, it would be heat. And that heat can often get out of control. So, for example, in the case of bushfires, we know that when something is set on fire, that fire can spread very quickly. In the case of fuel, fuel is something that's not like a natural disaster, like a bushfire. It can be produced at a fast rate, but when we're producing fuel, we can control that. So that's the only difference between a fire that would happen in the natural world compared to a fire that we're controlling, like a fire on a barbecue, for example. Okay, so that's the difference between the two, but both of those are examples of combustion reactions, although they're slightly different in terms of their properties there. Okay, so when we're talking about the combustion of hydrocarbons, we already said that carbon and hydrogen are the main things that are involved there in terms of what the hydrocarbons are made of. Hydrocarbons are the most common types of fuel used to produce energy. So you need to know that word hydrocarbon and what it is. Okay, so that's basically a repetition of the previous slide. Okay, so when we're talking about complete combustion, remember complete combustion is when we need plenty of oxygen, a lot of fresh air in order for complete combustion to occur. So when you're lighting a fire in the middle of a forest, that would be an example of complete combustion because you've got a lot of fresh air around you, a lot of oxygen, which allows you to thus burn those hydrocarbons or burn that fuel. Okay, so the main products of any complete combustion reaction are carbon dioxide and water. So if you see these two products coming out of a reaction that combines methane and oxygen oxygen are the reactants here, this would be an example of what we call as a combustion reaction. Okay, that's what a combustion reaction looks like. So that's a combustion reaction. Okay, we already know how to balance equations, so we're not too worried about that. So remember, whenever you're burning methane with oxygen, you always have two typical products that come out of that, carbon dioxide and water, and that's how you know that that's an example of a combustion reaction. Now, the opposite of a complete combustion is incomplete combustion. And that's just the chemical representation, the formula for that. Okay, now when we're talking about incomplete combustion is what we see in carbon monoxide poisoning. Okay, so when we're talking about incomplete combustion, we don't need a lot of oxygen for this to occur. So we need a limited supply of oxygen. So I'm putting an arrow going down. We can actually engage in incomplete combustion, or we can see incomplete combustion happening when there is very little fresh air in very closed spaces. Okay, and usually the products of incomplete combustion are carbon monoxide, which has a chemical symbol of CO, not CO2, and water, H2O. So if you ever see an equation with these two products, carbon monoxide and water, just know that that's an example of an incomplete combustion reaction. Okay, that's basically, and we already talked about what carbon monoxide is. We talked about, you know, people closing all the doors in their garage, turning on their car and kind of like suffocating to death, because carbon monoxide, incomplete combustion allows fuel to keep operating even in closed environments where there isn't a lot of fresh air, where there is a limited supply of oxygen there. Okay, now remember the difference between the two. Carbon monoxide, mono means one, oxide comes from oxygen. That's why it's only got one oxygen in its chemical symbol. Carbon dioxide, on the other hand, D meaning, or di meaning two, is CO2 because it's got two oxygen molecules there. So just be careful with your chemical symbols. Okay, they're not the same chemical symbol for both. Crude oil, well, this one's not so important, but you guys just need to understand that this is more of a theory-based thing, that all of our fuels, because all of them are examples of hydrocarbons, hydrocarbons are the most common type of fuel, always contain carbon in some form or the other. Okay, and we talked about this diagram where depending on how much we're heating up the crude oil, it can either form petrol, or it can form diesel, or it can form fuel oil, or any other oil that you have. Okay, so depending on how high or how low you're heating that oil, you will have an oil that will serve a different purpose than another type of oil. Okay, that's why the oil that you put for your barbecue, or the oil that you put in a truck or a tractor, is very different from the oil that we'd pump into our basic or normal cars. Okay, so that's the main difference. So just remember, our main fuels do tend to contain carbon because all of our main fuels that we use are examples of hydrocarbons, which are substances that contain both hydrogen and carbon as their main elements. Okay, yeah, this is just from the book anyway, but yeah, you just need to know what the combustion reaction usually leads to two main products of carbon dioxide and water. Okay, that's 4.6. Any questions?
Miss.
Yep.
I have a question.
Yes. Okay, tell me.
You know the combustion reaction? You know how water and carbon dioxide is always produced?
Yes.
What is always produced with precipitation? Is a metal salt and water?
Yeah, so with precipitation, no, that's you're talking.
That's neutralization.
Yes. Precipitation is usually an insoluble solid, which is our precipitate. That will be the product, as well as an aqueous solution. So aqueous solution could be anything. It could be a metal salt, it could be potassium chloride.
Okay, so it's not limited to one.
It's not limited to one, yeah. Anything that's an aqueous solution that's dissolved can be a part of that, along with the insoluble precipitate there.
So we should know neutralization, combustion, acid and base. Wait, Miss, isn't acid and base neutralization reaction?
It's acid base. One type of reaction that comes out of our acid base reactions is neutralization reaction. We've also got some other ones as well. For example, when an acid reacts with a metal carbonate or a metal oxide. So those are the other two.
Do we need to know them, those two?
Yes, you need to know the basic rule. Yeah.
Okay, fine.
How many more spreads do we have left?
Just two more. Okay, so 4.7 is pretty straightforward. It's just looking at polymerization. So we learned this one recently. So this is just talking about the different types of polymers. We know that polymers are a functional unit of plastic. In the same way, amino acids are the functional smaller units of proteins. Monomers are our smaller compounds of, or our smaller molecules of plastic. Okay, so monomers are the smaller ones. They're the single foundational basic units there. And when we join a lot of monomers together, we make up a bigger structure here called our polymer. Okay, a polymer is simply something that combines to form our plastics. Okay, and we know that plastics are very important for our world. We have three main types of plastics. You've got the linear polymers, which look quite straight. They kind of look like railroads. Okay, they're straight lines. Elastomers are quite flexible because they have the word elasto, similar to the word elastic. And cross-linked polymers are basically like a combination of the two. Don't stress too much about the overall structure. Just focus more on what polymers and monomers are, okay, what the difference between those two are. So yeah, I've already just talked about these two in the previous slide, what their main properties are. The same thing with cross-linked polymers. Thermo said this is quite important, so know the main difference between a thermoplastic and a thermosetting plastics. So thermoplastic, we said they can be softened quite easily and melted quite easily when you expose them to heat. Thermosettings or thermosetting plastics, on the other hand, are a little bit different. They are not easily meltable, okay, and they are quite solid and rigid. So even when you expose them to heat, they remain quite firm. They don't melt or become soft. Whereas thermoplastics, like a plastic bottle or a piece of Lego, they do become soft and they do become kind of melting in terms of their texture there. Okay, again, some more similarities and differences. So these two slides are quite important, okay, because I know a lot of you will get confused between the difference between these two. So just be careful because they sound similar, but they are different. Okay, when you think of the word thermoplastic, plastic means flexible, so just remember it that way, okay? Whereas thermosetting plastics are kind of set, they're solid, they're firm, they're set. They're not going to change if they're exposed to heat. So just maybe think of it that way. That might help you remember. Okay, the formation of polymers. So this is quite important. Okay, so you do need to know that polymers are made by this reaction called a polymerization reaction. Okay, this is when the small molecules of monomers that form a polymer are combined or integrated together using high temperature and high pressure, and that allows them to form the bigger molecules, which we know as polymers. Okay, polythene bags, we all know what polythene is. It's a type of plastic. It's normally used in bags and wraps and that kind of stuff. Polythene is produced using a polymerization reaction. Okay, so a polymerization reaction basically, and I did explain this in class. You're not going to be asked a random polymer that you haven't heard of before. If we ask you anything, it will be about ethene. So as long as you know what's on this slide, you're kind of all good, okay? So remember the chemical formula for ethene is C2H4. So we've got two ethene units here. This is unit 1, this is unit 2. So that's 1, 2, and then that's 1, 2, 3, 4. Okay, so that's basically representing that formula there. Okay, so because we've got 2, we combine 1, and then we combine another one. And that's showing that those two carbon molecules have a double covalent bond. So just draw the 2 lines there. Okay, so that's basically showing you how the polymerization of these two happen. Okay, so this is probably the more important one. Like I said, we're not going to ask you to draw this crazy diagram at the bottom, so you can just cross that out of your notes. But this part is important. You need to be able to understand the relationship between this chemical formula and the actual polymerization reaction and how that is visually depicted or demonstrated. So that's usually important, if not for the test, at least for the exam. It will be tested in some way.
Miss.
Yep.
So ethene is produced by
Which one? Oh, yeah.
polymerization.
Yes.
By
So just,
polymerization
yeah,
reaction.
polythene has a
How did it
molecule of
make-
ethene. Yeah. So just mainly know this diagram, not the confusing part at the bottom, but just this.
The top.
Just have an idea of how this links to this diagram here, how you can see 2 molecules, for example, of carbon and H4, so you can see 4H there, and then how those would combine to then form the polymerization. Okay, so that's basically the formation of polythene. And the use of polymers, this is very theory-based. Just know at least 2 examples of how polymers are used in our daily life. For
which type of polymer?
As well. Sorry?
Miss, which type of polymer?
Just in general, just this one doesn't specify which type of polymers are used for which. Just learn any 2. So they're used in polar fleece jackets, they're used in plastics, they're used in tents, any 3, any 2 or 3.
Okay, thanks.
4.8 is talking about the collision theory, and it's also talking about how we can increase the rate of reactions. So remember, when we're talking about rate of reactions, fast reacting or a chemical reaction that's got a rapid speed of reaction basically indicates that the atoms that are involved in that chemical reaction are colliding with each other at a rapid rate, and that is what is causing the increased rate of reaction. So in other words, I think I wrote that down somewhere, an increased rate of reaction equals to increased collision between the atoms involved in that reaction. Okay, we said that, remember, if you remember that video I showed in class with the boy and the girl running down the hallway, in order for two atoms or ions to collide with one another, in order for the reactants to form products in that chemical equation, we need to have two main conditions. Number one, we need to have the atoms in the correct orientation or position. Okay, they need to be angled in the correct way. And number two, you need to have enough energy for that reaction to occur. So in other words, the atoms, or in our case, the boy and the girl who are running down the corridor, need to be angled in a way that they will collide with each other. And they need to have enough energy to be able to run down the hallway in the first place. Okay, so that is basically the two important requirements for collision theory for a chemical reaction to take place. Okay, so increasing the rate of reactions, we know we can increase the rate of reactions by increasing the surface area of the reactant particles. This could be, for example, taking a big cube of metal and smashing it so it becomes like a powder. So now that's a more surface area. So you could, obviously there'll be more area on which the reactants can kind of interact or combine. Concentration of reactants means that we are increasing the overall concentration or the strength of the reactants involved, and the temperature. Usually as we increase the temperature of that particular chemical reaction, the reactants within that reaction will obviously start to gain kinetic energy, and they will start to move faster, and that will increase the rate of reactions by increasing the rate of collisions. They'll start to collide more rapidly with one another. Okay, and yeah, we talked about how increasing the concentration of a rate of reaction can actually increase how quickly the reactants will combine to form a product, as we see here. Okay, with the concentrated sulfuric acid and sugar reacting much faster than the dilute sulfuric acid. And yeah, I said that when you increase the temperature of a compound or a substance, obviously the atoms will gain more kinetic energy, which is energy to help them move. And as they have energy to help them move, they're going to move faster. And as you're moving faster, there'll always be a greater likelihood that the atoms will collide into each other, and that will increase the rate of reaction there. And the last thing in 4.8 was stir and mix. So as you said before, when you're stirring, if you put an acid and you put some, two compounds into a beaker and you just leave it there, they're not really going to interact. But when you actually go in and manually stir that up, that is going to help those two compounds or two elements to combine better with each other. Okay, so that is basically what stir and mix is about. Yeah, okay, that's 4.8. Okay, any questions so far? We just have one more spread to do and then we're done. No, all clear? All right, so then the last topic we looked at was catalysts, and we did this one on Friday, if you remember. Basically, you need to know that catalysts are just a substance that will speed up a chemical reaction without being used up in that particular reaction. Okay, an example of a catalytic converter that we have is the ones that we have in cars. They take toxic carbon monoxide gas, which would normally be quite dangerous for us, and they convert that into carbon dioxide. And they have to do it quite quickly, because when you turn on the switch in your car, or you put your key in the ignition, it needs to do that in a very rapid rate, so we're not like dying of monoxide poisoning within the first minute of turning on our cars. Okay, in order for that to happen, we have catalysts in our cars that actually convert that toxic gas into a safe gas that will not kill us. And we talked about catalysts as being kind of harmful for the environment because they do deplete the ozone layer because of the formation of chlorofluorocarbons, which is not super important for us, but you can just learn any two products in which chlorofluorocarbons are actually present. Okay, we call them CFCs for short. Don't worry too much about the environmental impact. Same here, it's not so important. Yeah, that's not, yeah, enzymes are biological catalysts. So usually our enzymes are an example of a catalyst that's in our body. And in order for us to, for example, digest particular food, the enzyme comes in and breaks down that food so that our digestion doesn't take a week, but can usually be completed within like 24 hours. So we do have enzymes in our body that speed up those chemical reaction rates related to digestion or related to excretion and all that kind of stuff, okay? Just as one lock will open one key, one enzyme will usually catalyze or open up one reaction, okay? So just remember that that one specific enzyme will usually act on one specific reactional function there. It's not like a one size fits all approach when it comes to enzymes. Okay, yeah, that's enzymes. 4.9, actually, most of it's not super relevant. And you would remember we didn't really go through the ozone layer impact in depth. That's more the environmental impact. Just know what a catalyst is and how similar to the other factors that influence rate of reactions, catalysts are just another example of a substance that speeds up the reaction. And most importantly, that it does that without being used up in the reaction and by lowering the activation energy that's required. Okay, so that's basically talking about catalysts. Okay, now that we've covered 4.4 to 4.9 in kind of like a summary, any other questions, any other topics in chapter 4? No, yes. Okay, so guys, what I'm going to do is tomorrow I'm going to give you guys a practice, like just like a booklet of like practice questions. It's just going to be similar to what you've already done. It's not going to be like a miraculous piece of paper or something that's going to help you for the test, but it's like good because it'll just give you some more practice in order to, I guess, get some more exposure to those types of questions. So yeah, you guys will be prepared for Wednesday in that case. Okay, obviously our test will be on EP on Wednesday, so just remember to bring your laptop nice and charged. Also, I did put up a post on Schoolbox about this, and I have emailed your parents again, reminding them that the style resource has to be purchased. So we just need to make sure we go in and purchase that as well.